This lesson presents the material from the first chapter, Building Energy Efficiency, the second topic, Building Envelope Efficiency, Lesson 4, General Evaluation of Building Envelope. This lesson presents the methodology for evaluating the overall energy efficiency of a building envelope. You will get acquainted with how to assess building heat losses occurring through building partitions, as well as those caused by cold air infiltration. You are already acquainted with the definition of U value from previous lessons, but this indicator is quite different from what we experience in everyday life. For example, how much we will have to pay for heating a building or which building to buy when there are similar choices. Increasingly, we are also concerned about climate change, and building heating has a significant impact on this process. In this slide, you can see statistics from recent years and the European target for 2030 in the field of building energy consumption. The blue columns indicate direct and indirect emissions from the operation of residential buildings, including both emissions generated directly in the building and indirect emissions due to the use of electricity and centralized heat production. The purple columns indicate the same values for non-residential buildings. This data shows that both residential building owners and governments will need to work and invest in building improvements if we aim to control climate change. So, how can we evaluate these final indicators related to our buildings? We will analyze building energy consumption starting from the U value and incorporating other necessary data. First, we will calculate the specific heat loss, H, which describes the actual building considering its architectural solution. Generally, heat losses must be compensated by internal gains, solar gains, and the heating system. Internal and solar gains are free, but the operation of the heating system is what we pay for and what generates co-emissions. The thermal mass, also indicated in the picture, acts as thermal storage for the building. It is very helpful when there is excess energy. It can absorb the surplus and release it later when the extra energy is needed. Therefore, when evaluating specific building heat losses, we will focus on calculating the heat losses that occur through building partitions and through natural ventilation or infiltration. Here, you can see the same information expressed using equations. To determine the specific heat loss, we need to know the thermal characteristics, U values, of the partitions, walls, windows, roofs, etc., and their areas, the thermal characteristics of building thermal bridges, psi value, and their lengths, and the amount of air that can infiltrate the building or be supplied for natural ventilation. Some of the variables, U value, partition area, you already know, and we will get acquainted with the unknown ones in the next steps. After evaluating the heat losses through the partitions by determining their U values and areas, as visualized in the top pictures, we also need to evaluate building thermal bridges, which are visualized in the bottom pictures. Thermal bridges are the connections between different or the same partition planes, where heat transfer is higher or lower compared with the adjoining partitions. Scientifically, thermal bridges involve two-dimensional heat transfer. This phenomenon is visualized in the next slide. A thermal bridge is a longitudinal element identified as the line where a floor meets a wall meets a window, in corners, and so on. The thermal characteristic of a thermal bridge is described by the psi value, which indicates whether we need to increase or decrease the calculated heat losses. Most psi values of thermal bridges are positive, meaning we add a small amount to the heat loss calculation. This share of heat loss might be very small, up to a few percent, for energy-efficient buildings but can be significant for older buildings, consisting of 20 to 30% of the total heat losses. Here you can see a visual explanation of what is evaluated when considering heat losses through thermal bridges and what happens if they are ignored. On the left side, there is a thermogram view of a real connection between a wall and a window. This picture shows how temperature is distributed in the cross-section of the window and wall connection. The picture in the middle shows how the thermogram would look if thermal bridges were not considered. We can see that the real situation differs, so evaluating thermal bridges is important for detailed calculations. There is also another benefit for civil engineers from thermal bridge analysis. In different connections, there are usually weak points in the building where the insulation layer is thinner or where thermally conductive materials cross the construction. Thermal bridge analysis provides information about temperatures at different points in the construction, allowing us to check if any points have a temperature lower than the dew point inside the building. Avoiding temperatures below the dew point prevents condensation on the constructions and the growth of mold. Of course, humidity and mold often occur because of cracks in the building, but poor connections can also be a contributing factor. The last parameter that remains unknown from the equation on slide 5 is related to the heat losses caused by heating the cold air that enters the building. The heating system is responsible for this task and consumes energy. These heat losses are directly dependent on the volume of cold air, V. In most cases, this volume consists of air supplied to the building for natural ventilation purposes, as well as cold air infiltrating the building through micro-leaks. The amount of air necessary for ventilation is defined in hygienic norms and varies slightly between countries. Average values also fluctuate depending on the purpose of the building, but generally it can be assumed that for buildings where normal or low physical activity takes place, 20 to 25 cubic meters per hour of fresh air per person is required. For light physical work, 45 cubic meters per hour per person, and for intensive physical activity, 60 cubic meters per hour per person. Knowing the number of building occupants, we can easily determine the volume of fresh air that will enter the building through natural ventilation and will need to be heated by the heating system. Sometimes the exact number of occupants is unknown, but the building size can be used as an indicator. In such cases, an air change rate per hour can be applied. This may start from a level of 0.5 air changes per hour, meaning that half of the building's air is replaced during 1 hour. In the case of natural ventilation, air enters the building through opened windows and doors, outdoor grills, and vents, and leaves through ventilation stacks or also opened windows and doors. Natural ventilation occurs due to the wind's impact on the building and the density differences between warm and cold air, which cause the air to move. In addition to natural ventilation, which is intended and designed to exist in the building, there is also unwanted air circulation called infiltration. Cold air infiltration into a building occurs through unintentional gaps, cracks, and openings in the building envelope. Common areas for cold air infiltration include zones around windows and doors, improperly sealed sills, gaps and cracks where walls meet the foundation or roof, and any holes in walls, floors, or ceilings for plumbing pipes, electrical wiring, or ductwork. These are all potential sources of air leaks. The general property of a building to resist infiltration is called building airtightness. The building airtightness indicator shows the average air change rate in the building when a 50 pascals overpressure and vacuum are applied. This indicator is called the N50 value. Buildings with the highest energy efficiency ratings should not exceed an air change rate of 0.6 per hour, N50 value, while buildings with the lowest efficiency may have airtightness up to 50 air changes per hour. The N50 value is determined through experimental testing, known as a blower door test. During the building design stage, a target airtightness is sought by applying various engineering measures, mainly proper sealing of partition connections. When considering the airtightness features we are planning, we can use this value to calculate the volume of infiltrated air according to the equation presented in the slide. Here, 0.25 is a coefficient accounting for the fact that air infiltration does not occur over the entire envelope area. N50 is the value of the air exchange rate in the building, determined by tests. 0.75 is the aerodynamic coefficient of the building. AI is the air density, that is 1.21 kilograms per cubic meter. 0.9 is a coefficient for the reduction of wind speed due to the presence of various barriers around buildings. Wind is an average wind speed in meters per second. 50 is the pressure in pascals at which the airtightness of the building is measured. V is the volume of the heated space of the building in cubic meters. N is the value of the degree index determined by blower door tests. After performing the previously described calculations, we already know the building H value, which describes the overall building envelope efficiency by indicating the thermal power in watts that needs to be supplied to the building to decrease the indoor temperature by 1 degree. This value is easily understandable when comparing different buildings, but it does not account for the climate of the region where the building is located, because the same building in Spain and Finland will require different amounts of energy to achieve the same thermal comfort during the heating season. For this purpose, the concept of heating degree days is used. Heating degree days measure how much, and for how long, the outside air temperature is below a chosen base temperature, usually from +18 to +22 degrees Celsius in Europe. The base temperature represents the indoor temperature below which heating is needed. Each degree below the base contributes 1 degree day per day. Heating degree days is a climate indicator used to estimate the heating demand for buildings. When we know the specific heat losses of the building and the heating degree days of the building location, we can estimate the thermal energy consumption for heating, which is nearly equal to the thermal energy losses. For more precise results, internal gains, free thermal energy sources within the building, should also be considered. However, evaluating internal gains is not very relevant when determining the best engineering solutions for building envelope efficiency, so they are usually not considered during the building design stage. In this slide, you can see European Union statistics on heating degree days, which primarily reflect climate differences. From this, we can conclude that a building in Portugal might have 3 times lower specific heat loss values compared with a building in Lithuania, yet still require a similar amount of energy for heating due to climate differences. The picture on the right shows how the average heating degree days have changed since 1979, reflecting the trend of increasing temperatures. Once we know the amount of energy needed for heating in kilowatt hours, the final step is to multiply it by the price per kilowatt hour. Different energy sources can be used to produce thermal energy, which is the most basic form of energy, so prices vary significantly. Thermal energy can be generated using biomass, logs, coal, oil, gas, or electricity. Prices also differ between countries depending on the availability of energy sources, and political factors can have a major impact as well. In addition, the equipment used to convert the primary energy source into usable thermal energy has different efficiency ratings. In this slide, you can see the range of energy prices in various European Union countries for different thermal energy sources. Finally, we would like to highlight one more important aspect. When discussing climate change, a more critical indicator than energy price is the co-footprint associated with different thermal energy sources. As shown in the data on this slide, even if the prices of thermal energy from various sources are similar, since they must be competitive in the market, the carbon footprint can differ significantly. This means that not all kilowatt-hour supplied to buildings have the same impact on our planet. In this lesson, we presented simplified calculations that allow non-professionals to understand the main principles of building efficiency. In real-case scenarios, the calculations are more complex and usually performed by certified engineers. Thank you for your attention, and follow the next lesson number 4, where you will get acquainted with how to evaluate building energy efficiency, knowing all the information about its partitions and the construction materials used to build them.